Hello, my name is Mark Gibson, and you're listening to the podcast version of the Teagasc Signpost Series, a weekly webinar that promotes and examines sustainability in Irish farming. Very good morning, ladies and gentlemen. You're very welcome to our 103rd episode of the Signpost webinar series. I hope you're keeping safe and well wherever you're joining us from today. The series is brought to you by Dairy Sustainability Ireland, the National Rural Network, and Food Drink Ireland SkillNet. And this week, the Intergovernmental Panel on Climate Change launched its sixth assessment report. And it said that in 2010, between 2010 and 2019, average global annual greenhouse gas emissions were at their highest level in human history. But the rate of growth has slowed. And without immediate and deep emissions reductions across all sectors, limiting global warming to 1.5 degrees centigrade is beyond reach. And very appropriately today, we will be discussing how we can reduce the carbon footprint of cattle and pig manure. And we're delighted to be joined by Stephen Nolan, who is Field Research Lead with Glassport Bio, and Shaun Connolly, who's a PhD with NUI Galway and Teagasc. And you're both very, very welcome to the Signpost webinar. So maybe, Stephen, if you could give us a short overview of this project. It's very timely, and obviously pig and cattle slurry are both very valuable, particularly in the last number of months to farmers as a fertilizer, but also what we want to talk today about is how we can reduce that emission factor from these slurries.
So I've done some time with Teagasc. I have a degree in agriculture, and I've more recently completed my PhD in environmental microbiology, and as part of that, I've done some work on greenhouse gas abatement from agriculture with Glassport Bio, which is a spin-off company, a startup based out of NUI Galway. We're doing some work with Teagasc, which we're going to introduce today. Shaun is taking that on down in Johnstown Castle. So it's just good to present some exciting research and results that we're producing in Ireland to tackle greenhouse gas emissions from agriculture and do more sustainable agriculture in general. So
great. Thanks, Stephen. And Shaun, where are you coming from today?
Currently in Galway. Yeah, just back in NUIG right now. But for the last 2 years, I've been down in Wexford in Johnstown Castle, and I've been completing or close to completing my PhD, studying gaseous emissions from cattle slurry. So a lot of the work I'll be presenting here today will be a lot of my PhD work. So hopefully you'll find it a little bit interesting at least.
Great. Oh no, we're looking forward to it, and best of luck with your PhD. I'm sure you can see the summit now at this stage.
Exactly.
Great. So Stephen, I think you're going to lead off, and we will hear a short presentation from you, and then we'll take questions. So Stephen, we will ask you to share your screen, and we will talk to you after the presentation.
So like we said, we're presenting some research based out of Galway and Johnstown Castle in Wexford. So we're looking at climate change in agriculture, and I'm working with Glassport Bio, which is like I said, a startup in Galway, and our lead product is what we've called Gas Abate, and it's there in the title. The intention is to abate greenhouse gases from agriculture. Within that, we have two projects that we're presenting today. One is funded by the SEAI, and we've called that GEBTech. It was our initial effort at looking at cattle slurry and reducing greenhouse gas emissions, with the view to improving the potential for renewable energy production from slurry. And following on from that, then we applied treatment to pig slurry, and we've titled that the PIGergy Project. So we're going to present some results from that today as well. So as most of us are aware at this stage, the greenhouse gas emissions from agriculture are significant across the world, and even more so in Ireland, where 37% of greenhouse gas emissions come from agriculture specifically. within that 37%, approximately 25% come from manure management and enteric fermentation. And this is where Glassport Bio is looking to tackle first and foremost. The approach of some people will be to say that we have to just stop producing animals and beef and meat and dairy even, and that we should just all go to being vegetarians. That would have significant impact on the rural economy and on livelihoods in the countryside. But we do recognize that we want to produce meat and beef and dairy as sustainably as possible. And so to do that, the first step we see is tackling manure management. It's probably the easiest step to address. And then Glassport Bio are looking at feed additives to reduce enteric fermentation as well, because that's a bigger chunk of the pie, as you can see there. So the problem with gaseous emissions during manure storage is that while the manure is being stored, it's constantly emitting ammonia, methane, some toxic gases as well. And during those emissions, you lose nitrogen value, you lose carbon to the atmosphere, and once that's lost, it's no longer valuable and it can't be returned or recovered and applied to land. So that results in increased mineral fertilizer purchases, and where anaerobic digestion is being used to produce energy, it results in a lower energy output from the slurry. There are also some health and safety risks around stored slurry that the farming community is well aware of, and of course it contributes to the total greenhouse gas emissions from agriculture. There are some steps that can be taken to mitigate emissions from stored slurry. Primarily, they're expensive, so they revolve around covering storage or applying acid treatments, sulfuric acid or different treatments, and some of them are ineffective. Some of them reduce either carbon emissions or ammonia emissions, but none of them prevent both carbon and ammonia emissions. So if, for example, if you cover a lagoon, you'll reduce ammonia emissions because there's less wind flow over the surface, but you will create an anaerobic environment that is conducive to producing more methane. So so the current treatments are ineffective or expensive or both, and can cost up to €5 per ton of slurry treated without producing any net benefit to the customer or to the farmer. So our solution, we've called it gas abate. We have a few different application types. So in smaller applications, you could have a slow release block, or in bigger storage tanks, we could have automatic dosing pumps or hand applied pumps. And the aim of the treatment is to target methanogens. So methanogenic archaea are constantly producing methane in anaerobic environments. So we look to inhibit that microbial gas production. And in so doing, you reduce the bubbling of gas up through the slurry and reduce other gaseous emissions as well as just the methane. What we've seen is a 95% reduction or up to 95% reduction in greenhouse gas emissions during storage. So the benefits of our approach is that there aren't big startup or implementation costs. It's relatively simple and straightforward. And by retaining the nitrogen in the slurry, we've seen that we can lead to reduced fertilizer purchases, and by retaining the carbon in the slurry, if the slurry is then being fed to anaerobic digestion, it can be up to 38% of an increased energy output. There are some other benefits there around carbon credits and reducing the carbon footprint of the supply chain, which a lot of corporate or say retail customers are looking for. And at some point in time, there will be this tradable carbon credit schemes. coming into play. So how it works is it's applied to liquid manures or slurries in storage tanks or in lagoons, and it's a product of a reaction of two active ingredients. So they work together to produce an inhibitory agent that targets methanogenesis specifically and reduces methane production in storage. It creates an environment that causes them to shut down for a period of time. It's not a biocidal agent. It doesn't kill them, but it inhibits their activity and thus prevents production and release of methane, and by extension, biogas and other gases to the atmosphere. The benefits are obviously greenhouse gas reduction in the ag sector, which is the primary benefit. But there are some secondary benefits, particularly where anaerobic digestion is being applied. I also work with an anaerobic digestion plant in Kildare. And so we see that by using slurry that's been treated, you can get an improved biogas yield. Slurry is notoriously low value for anaerobic digestion, so you want to retain as much of the potential methane yield as possible. And then, like I said, we can see an improved nutrient value, so sulfur and ammonia in particular. And in applications where enclosed housing, especially for pigs, there's some animal welfare benefits where they're in close contact with high levels of hydrogen sulfide being emitted from the slurry, and if you can reduce that, it's positive for animals as well. So currently, as we know, what happens is the manure is emitted or captured in storage, and then during storage, greenhouse gases are produced. And as the greenhouse gases are produced, you lose the nitrogen and carbon value of the manure. That manure is then spread on fields as fertilizer, but it's a low value fertilizer by the time it's spread, if it's kept in storage for any length of time. And the same if it's fed to digesters for biogas production, the carbon content is gone from it. We aim to treat the manure in storage then and reduce greenhouse gas production so that it's a better fertilizer and a better feed for AD. So I'll introduce you now to Shaun, my colleague, who is going to present his work on GEBTech based in Johnstown Castle. So
great. Thanks very much, Stephen. And thanks everyone for joining today. So I'll be talking you through GEBTech, my project from a PhD. It stands for Green Energy Boosting Technology. It's a novel treatment for farm slurries to reduce greenhouse gas emissions and then further downline implications of generating more energy for anaerobic digestion through that inhibition of methane. So worldwide, there's just under 1 billion cattle, and it's the largest livestock group on Earth emitting greenhouse gases from both enteric fermentation and manure management, as Stephen was going through earlier before. In 2018, we were awarded an SEAI grant. And today I'll just kind of be talking you through the lab scale trials up to the medium scale trials, and then finally up to the larger scale trials that included a commercial farm. And what we want to achieve from these experiments is essentially a carbon enhanced manure feedstock that we can then bring to an AD reactor, increase the biogas yields, and then from that use the digestate as a fertilizer. So next year I'll just move on to the lab scale trials here. So essentially here we have our untreated slurry in green, and what we're trying to do here is, if you can just click next there, Stephen, we can see that we have small scale trials ranging from 10 grams to 2 kilograms. So we have varying concentrations used here, and we can obviously see that the gas abate dose 3 here is inhibiting the most amount of cumulative methane. We have compiled a data set based on the concentration, the frequency, and the different sources that the reagent can be applied in. And this was kind of the optimization part of the project. Next, we moved up to these kind of 2 kilogram mesocosms here. So we have a 1.6 kg experiment measuring ammonia emissions in this current picture down here with the yellow lids. And this is also a very big portion, very big part of the project was ammonia emissions, methane emissions, and a lot of the different gaseous emissions trialed. So we had cumulative methane emissions, and that was optimized for the additive formulation. And we saw a marked reduction in methane production at all rates. And the effect we found was dose dependent. So the higher the concentration you used, or the higher dose you used, the more methane inhibition you actually or was actually seen from the slurry. So we'll move on to the next slide there. And again, this is just another kind of small scale trial. And this is again more cocktail optimization. So again, if you can see here in the green line here, that's an untreated slurry. And essentially we wanted to determine how best to add in our additive, whether to add it in as a powder, a liquid, a pellet. All we saw was that there was very little difference. You can actually see the different formulations up here. The liquid, powder, and pellet up on the top right hand side here. And this is a picture of the actual trial in which the biogas was actually captured from the slurry post treatment, and then the biogas was actually tested afterwards. And again, there's no appreciable difference as long as you treated the slurry with the additive. You saw a marked reduction in the biogas and methane values. We also had a independent trial carried out in Germany, as you can see on the bottom left here in these black containers. And what they saw was they saw a 95% reduction in gaseous emissions from the storage when it was treated with our treatment. These were held in 25-degree storage tanks, and biogas production was measured from both the treated and untreated slurry. And again, we saw this huge reduction in the biogas production from the slurry. And then as a result from that, that enhanced carbon feedstock was also trialed in an anaerobic digester, also in Germany. And those results would be presented near the very end of my slides. So next we'll move on to the medium scale trials. These 15 kilogram drums, and these were held for 10 weeks, a 10-week period. And what we saw was that in these 4 different treatment phases, no or very little gaseous emissions were actually measured during that time. Apart from treatment phase 1 after about 10 days, you can see. So these were held at 15 degrees Celsius. The manure solids content was 4%, and we were measuring greenhouse gases and ammonia emissions from this. But we were also interested in the slurry characteristics like the pH, the redox potential, dissolved oxygen, and all these factors help us determine how the treatment is actually affecting the slurry. So we saw a 92% decrease in the total biogas emitted from the slurry during storage, and that resulted in an 88.6% reduction in the total methane emitted from the slurry also. And next we'll move on to my own experiment in Johnstown Castle here. So we had 9 1 meter cubed tanks, and we filled that we filled them with slurry essentially, and then we wanted to treat those tanks with the exact same treatment. So we were again going for the same kind of testing regime, so greenhouse gases, ammonia. But we also wanted to test hydrogen sulfide, pH, redox potential. So over here you can see the tanker on the left actually filling these tanks. The tanks being the tanks when they were full, and then some of our measuring equipment down at the bottom here. So our redox potential probe, the lid that was testing some of the greenhouse gas emissions, and then over here those glass tubes measuring ammonia. And what we saw was that the hydrogen sulfide emissions post agitation, obviously where the majority of the H2S emissions is actually seen, we reduced that by about 80% post agitation, and that was purely from our treatment. Our ammonia was reduced by 50%. Our nitrous oxide emissions were reduced by 85%, which is very unheard of with slurry. We don't really think of nitrous oxide emissions when we think of slurry. And also our methane was reduced by approximately 40%, as you can see in this graph just down here. So the red and blue are our treated slurries, and then our control slurries. Our control slurry is up here on 800 grams per meter squared. And then these are just some of the graphs from the exact same trial. So our N2O emissions from that same trial. You can see in this gray line here, our control slurry producing lots of N2O. But no matter what you actually did, or when we actually added in our treatment, the gas abate or the gas abate plus calcium chloride, which is a nitrification inhibitor, we saw huge reductions in the N2O production from the slurry storage. We also see, and again, this is the same with the H2S emissions. You're okay, don't worry. From the H2S emissions, further 80% reduction post-agitation once you treated the slurry. So then we wanted to test how this actually affected the AD process. So again, we went to Germany in that same trial that I mentioned before, independently verified anaerobic digestion trial, in which treated and untreated cattle slurry was used. And what they saw, there was a 38% increase in the biogas output from the treated slurry compared to the untreated slurry. Next, we also had triplicate 10-liter bioreactors in NUIG. This is a picture of them over on the right-hand side here. And this is run in a continuous anaerobic digestion format. So these were co-fed cattle slurry and food production waste or grease trap waste, whereas the graph on the left was only a monodigestion. But again, it was a fairly similar story with the 10-liter bioreactors, where we saw an average methane increase of between 14 and 18% when we used treated slurry versus untreated slurry. Next, again, if we're not going to be bringing it to AD, if we actually just spread it, what happens? So we wanted to test the fertilizer potential of the treated manure. So on a small scale, we had small scale agronomic pot trials of perennial ryegrass treated with untreated and then gas abate treated manure. And we saw a 15% increase in the dry matter content of the grass. And the grass is harvested at week 3. And we also saw an enhanced sulfur concentration in the treated slurry. And then that also mapped over onto the grass very well. And you can see up here on the top right, these kind of greener samples. And this is also very important. If you decrease your H2S emissions, your sulfur content goes up in your slurry. And then that paper down on the bottom of that slide, Claire Aspel's paper from also Johnstown Castle, kind of goes over the nitrogen use efficiencies of increased sulfur content and decreased nitrogen leaching from soils. Very, very interesting paper if anyone is interested. Next, we wanted to go on to a commercial dairy farm, a kind of full-scale trial where we wanted to test the additive in its kind of its largest form. So this farm had 220 cows and 3 tanks, ranging from 485 to 590 meters cubed of slurry in total. So as you can see over here with this gray arrow on the very top of the graph, this is our baseline data. As you can see, you get some peaks with the methane data, but as soon as we add in the GEBTech, the gas abate application here in red, you can see a marked reduction in the amount of methane actually emitted. So again, we get a 78.6% reduction in the methane output once we actually added in the gas abate product. Move on there, Stephen. Thanks very much. Finally, the Glassport team did a climate impact forecast on a theoretical farm, a 2,000 cow intensive farm in Germany. So this German farm, this theoretical farm, had anaerobic digestion on site for electricity, in which 100% of that was used, and then heat energy, of which 50% was used. and the farm has a use for the digestate as a fertilizer also. So the climate impact, or the climate impact forecast from the EU, this tool that we use from the EU, includes the gas vape production, the production of the gas vape products, the transport of the components, the fertilizer transport, the emission of the slurry management, the emissions from the gas vape pumps, the biogas output, or the increased biogas output from AD, and the ammonium content of the digestate following the gas vape tree manure. And what we can see is that there was, sorry, no, just hit next there again, Stephen. There you go. You can see a 3.7 kiloton saving in CO2 equivalencies, and this is equivalent to 3,700 potentially tradable carbon credits for a farm if they do end up being tradable. So again, it's a very huge saving in terms of carbon, and something that can be looked to for the future to actually save on carbon and potentially a new income source for farmers. So I'd like to thank you all for your attention. I'll hand you back over to Stephen, who will be talking about PIGergy.
Okay, thanks, Shaun. So having successfully looked at cattle slurry and treatment of cattle slurry for reducing greenhouse gas emissions, we wanted to apply the treatment to pig slurry to see if we would have a similar effect. And so we titled this project PIGergy. There's 677 million pigs worldwide. About 1.6 million of those are in Ireland. So we've carried out some research on Irish pig farms to see what we could see. We started off though with laboratory scale trials again, just testing pig slurry in the lab and under different treatment doses and cocktails. And we scaled that up through medium scale and now onto larger scale on-site trials. Again, we considered the potential for the manure feedstock to be enhanced for biogas production and anaerobic digestion, BMP being biomethane potential there. So the lab scale trials consisted of started at 10 grams and scaled up to 1 kg of slurry using varying concentrations of product and assessing the methanogenic activity. We saw from the start that there was some treatment effect, again varying with dose variance and inhibiting methane production at the early stages of storage. So we scaled this up to 16 kilos in 25 liter drums and ran a trial for 250 days, which took in the start of COVID. So these trials were carried out in my own shed under controlled environment, so that I could keep monitoring them while the labs were closed. We saw some significant results from that, more dramatic than with the cattle slurry for sure. So biogas production was essentially shut off for a long period of time, about 200 days, and it recovered towards the end. Within that, CH4 was also dramatically reduced, and so CO2 was similar, while H2S was dramatically reduced at the start, and H2S production then recovered after about 100 days, and similar effect for ammonia. So we tested a lot of different things that we had done with cattle slurry, and saw like a 90% reduction in biogas, a more significant reduction even in methane. So of the gas that was produced, less of it was methane, more of it was CO2. We saw a reduced 43% reduction in total in ammonia, again most of it in that initial 100 days, and the same with hydrogen sulfide. We then wanted to scale that up, so we went to IBCs, 1 meter cubed IBCs. We put about 750, 770 kgs of pig slurry in there. We used heat jackets, as you can see in the picture on the right there, and we tested it again. And again, we saw dramatic reductions in biogas production over the course of the trial. 77% reduction approximately in biogas, and again, even more significant reduction in methane. So what was interesting in this trial though is that after a week we tested odor producing compounds and saw a dramatic reduction in odor producing compounds. And anyone who's involved in the pig industry would be aware that in order to increase capacity or to even review licenses or any of that, odor is a massive concern for pig farms. And so the ability to reduce odor production from stored slurry is significant beyond just greenhouse gas emission reduction. We then tested that slurry in lab scale trials just to get a feel for the impact that treatment had on biogas production and anaerobic digestion downstream. And we saw a 46% increase in biogas yield from treated slurry compared with untreated. And of that biogas, there was a higher concentration of methane, which is important for biomethane producers, of which green generation will be the only one in the south of Ireland at the moment, the only one injecting biomethane into the grid. But so a 60% increase in biomethane production is again very significant. So we applied the same climate impact forecast tool as Shaun demonstrated earlier with cattle slurry, and we took a large pig farm in an Irish context with an AD plant generating biomethane, and assumed a use for the digestate, which digestate is used as a fertilizer for tillage crops around Kildare and Niue for sure. And so when we applied the same tool, the carbon footprint reduction wasn't as dramatic as it was for the cattle slurry farm, but it was still significant. And we saw per ton of slurry treated, you get a 52 kg of CO2 equivalent saving, which amounted to 839 tons of CO2 equivalent saved or mitigated in the context of a large Irish pig farm. There's some equivalence there to make it understandable for everybody. So I'm not sure how elephants get in there are relevant in an Irish context, but anyway, they're there anyway. So the next phase of that is to look at the potential for trading that saved carbon in terms of carbon credits, and that's something we're working on in the background, which will make it much more attractive to everybody involved. So Glassport Bio have a couple of other projects in the works. SEAI have funded the scale up of the pig treatment to large scale. We have an industry academic partnership and with an aim to market launch in 2024. We have trials planned for Ashley's pig farm in Waterford. They have an associated AD plant, so we can verify our findings at full scale. We have also received funding from the EIC for scaling up the cattle treatment to market. And the aim is to launch that in 2024, initially in Ireland, and then looking further afield than that. So that's our work, and thank you for listening. We'd welcome any questions you'd have.
Thank you, Stephen, and thank you, Shaun. Really enjoyed that presentation. Really innovative work that you're doing there with Glassport Bio, Teagasc, and NUI Galway. And lots of interesting questions coming in there. Just remind people, if you do have a question for Shaun or Stephen, please do use the Q&A tab at the bottom of the screen. I suppose from my own perspective, just looking at the work that you've done and the testing that has been done, how far away is this from being commercially available, or is it available now to farmers?
So the intention is to validate our findings at full scale in the next year. We're working on that, and then we'll be looking to launch in 2023, 2024. So in the next year or two, we'll be looking to launch to market fully.
Brilliant, brilliant. I'm sure I see there's quite a lot of interest from our colleagues in the Department of Agriculture joining us today. I'm sure this is a potential game changer when it comes to reducing emissions. Just in terms of those figures that you presented there on the CO2 equivalent reductions, I think it was approximately 100 kg per ton with cattle slurry, and was it 52 with the pig slurry? What does that equate to in overall percentages? What as a percentage difference with and without the additive?
So it came to about 85% reduction in biogas, 85 to 95% reduction in biogas production. So obviously methane is a significant component of the greenhouse gas emissions from agriculture. So if you could reduce greenhouse gas emissions from slurry by 85% even, that would be, if it's about 3.5% of the total, you're looking at a 3% reduction in the Irish context overall. So that in itself is a massive step towards our total greenhouse gas emissions and reaching targets. The next phase of that obviously is then to look at the feed additive side of things and reduce enteric fermentation emissions. And that's something we're working on in the background as well, with Teagasc and NUIG. So,
and in terms of how somebody would implement this on their farm, I know you showed us slides there with a device there that does it. Is it a slow release? Maybe could you just talk us through that a little bit?
Yeah,
so how that would actually operate?
For sure. So we looked at,
does it require specialist installation as well, do you think? Maybe it's a bit early to say that, but
yeah,
just from your own view on that.
So we've looked at a couple of different options. One of them is essentially a briquette type thing that you'd throw into the slurry tank and it would slow release over time. Another option, we have an engineering lead on that who's looking, especially in pig slurry context, of injecting. So it's a fairly simple setup with some pumps that would inject the treatment. And so when you see the biogas production starting to recover, it would be smart and essentially inject and dose treatment as it needs to every 10 days to 2 weeks. Once that, it would be fairly cheap to install it. It's not a complex system, and once it's installed, it would just sit there and work away in the background. The farmer or the user wouldn't necessarily have to have too much input into that. So we want to simplify it and make it as easy as possible for people to use, so that it's applicable. Yeah.
Shaun, you talked about increased sulfur concentrations in the slurry. How does that work? I mean, is there not the fixed amount of sulfur there, or is there an availability issue there that the process is affecting?
Yeah, so when you start off with slurry, there is a finite amount of sulfur within that. However, when that gets mineralized to, let's say, sulfate, that would be reduced to H2S. So H2S, sulfur. So if you can reduce your H2S emissions by 80%, or we're looking at actually increasing that also. If you can reduce it by 80%, you're not actually going to be losing a lot of that sulfur from the slurry. So from what we found, there was a 4 or 5% decrease in the sulfur content with slurry over maybe a 40-day period. So by actually using this treatment, you can actually keep that sulfur within the slurry.
Very good. And just on that hydrogen sulfide piece, I mean, there is a farm safety risk there with hydrogen sulfide release during agitation. Is that something that you would see having reduced risks there from a farm safety point of view?
Absolutely, yeah, absolutely. Like when you look at farm safety as a whole, like H2S emissions are, it's one of the first things you learn about as a farmer, to stay away from slurry tanks when they're being agitated. So if you can reduce that risk, that would be a huge thing for Irish farmers and farmers in general. Yeah, absolutely.
Thanks, Shaun. And just to Stephen, has there been any estimates of the costs of such a system or such an additive for farmers, or have we any idea where that's going to be pitched at?
Yeah, so we have some early indications, but until you commercialize it and produce it at scale, you're looking at small volumes and having to. So the price we're paying for the treatment just now wouldn't be the price in when it comes to market. So I think it's too early to say exactly, but it would have to make sense for the farmer, and it would have to make sense for all involved. So it wouldn't be prohibitive for sure. So.
Okay, thanks very much. So we'll just go to some audience questions here. I don't know if Pat is around there, but he's possibly taking an important call. There you are, Pat.
No, I'm here listening.
Yeah. Just there is a question there around the temperature dependency there on the additive to work. If either of you would like to take that one.
So we wanted to challenge the treatment. So obviously at lower temperatures, you get lower emissions. And so it would be easier essentially for the treatment to be more effective because there's not as much of an activity that it has to address. So for example, in the Kaiserslautern trials, you saw it was at 25 degrees. So at 25 degrees, you're getting a lot of emissions. The methane conversion factor is fairly high at that stage. In an Irish context, the temperatures will be lower, and so whatever effect we're seeing at 25 degrees will be exaggerated and magnified at lower temperatures. For stored slurry in a pig farm context, for sows, the temperatures maybe are at 20 degrees in the sow house, so the slurry is actually quite warm underneath the sows. So maybe 17 degrees. And so you do have about a 32% emissions factor there for slurry under pigs. And so we want to be sure that we can tackle that higher temperature. The temperatures under weaners then will be even higher. So we've used those heat jackets on the IBCs to make sure that we're seeing the same effect at higher temperatures as the lower temperatures. So.
Yeah, that fact alone that emissions are higher when temperatures are higher is interesting. I wasn't aware of that. That probably has implications for above ground versus below ground storage. Sure, and yeah, like you described there, the different types of slurry or housing systems that are there. Pat, a lot of very relevant questions coming through here.
Yeah, and I suppose one of the first ones is just what is the active ingredient, or what is the methodology of
secret sauce? Is that the phrase you're asking for, Pat?
It's just two compounds that are commonly available, but when they work together, they react with each other and cause an effect. Obviously, it's early days, so we want to keep that to ourselves just now. But okay, they're safe compounds. They dissipate rapidly in the environment, so there's no environmental concerns. They've been approved by the Irish authorities as non-biocidal, so they're safe and clean.
Yeah, because the issue of safety versus some of the other products that are being talked about, some of the acids in particular, I think are making farmers very nervous of what's down the road. So I think that's a real positive. One interesting question we have flagged now in the medium term a potential requirement to cover stores. Do you see this as a potential alternative treatment that might replace the need for that to happen?
Sure. Well, covered stores, so it's a requirement in some places already. So there is a benefit to covering tanks. The issue with covering is that it's extremely expensive relative to the size of the tanks. So there's a huge capital expenditure there, and it doesn't do anything to stop methane production in stored slurry. In fact, it encourages methane production because it creates an anaerobic environment. It is effective for ammonia reduction. So there's nothing to say that this treatment used in conjunction with covered stores wouldn't be a good option. But in the short term, for sure, this is much cheaper and and it's effective at both methane and ammonia reduction. But I think we are heading towards a case where for sure all kind of new facilities will be required to have covered storage.
Okay.
And possibly even refrigerated storage, which again is expensive to install and has a significant cost of operation as well, as you could imagine.
Yeah, there's a question in there about the potential for AD when you're suppressing the methane. What's the reversal process to try and make sure that you can then get the methane out of it? Is there any?
It's a good question. There? Yeah, it's a good question, and we've spent a lot of time thinking about this. So essentially, the treatment wears off after a certain amount of time. So it depends on your storage period before going to AD. So if you know that the slurry will be stored for 10 days and then eventually it'll be fed into anaerobic digestion, then you would treat accordingly. If you know it's a shorter period of time, you would also treat less, and then there will be repeated treatments if you're going to store it for longer. We've seen then that once it is stored, it doesn't negatively affect the methanogenic population in the anaerobic digesters either. So we haven't seen an inhibitory effect in anaerobic digestion itself. What we've seen is that the first couple of stages of anaerobic digestion, so the hydrolysis and the acidogenesis, proceed as normal. So the slurry starts to degrade and break down, but we inhibit the final stage of anaerobic digestion, and so actually it's a much better feedstock. It's almost more ready to go than slurry that's just been degrading over time in a storage tank. So yeah, it's actually positively affects anaerobic digestion as far as we can see.
There's a question here, Stephen, in relation to agitation, and I think you mentioned that there was a reduced agitation time required for slurry that has this treatment, according to this questioner anyway. But is there, without the methane gas bubbling up through the slurry, is there a risk there that there would be a greater crust being formed on the top of the tank? So I don't know, have you looked at that?
Yeah, so we have to see the dynamics in full scale tanks for a start, but crust, even if there was a bigger crust being formed, crust formation is one of the key ways of actually eliminating some odor and ammonia emissions from stored slurry. So even if there is a better crust being formed, then it's actually a net positive. Okay,
very good.
There's a question there about dry matter of the slurry, and I think the example you took looked to be a very high dry matter slurry, but I suppose a lot of slurries at farm level, particularly I suppose on dairy farms, tend to have a lot of water coming in, and on pig farms, depending on the feeding system, can vary significantly. So what's the impact of that, and is there issues around the economic viability of the use of the product where you might have low dry matter slurries?
Yeah, so again, the idea with using high dry matter was just to challenge the treatment. Obviously, if there's more volatile solids available to the methanogens, then you're more likely to get a bigger volume of gas coming off. We have tested a variety of different dry matters range, and we're settling on about 8% solids for dairy slurry, just as kind of nice happy medium of where we're at. So we're testing a range of temperatures and a range of dry matters. So pig slurry, I work with a pig farm here in Kildare, and the pig slurry will range from 2%, where there's a lot of washing going on, to up to 4.5% for weaners. So we're very aware of the different ranges, and we're looking at treating all ranges. We did want to really push the product and test it at temperature and with higher dry matter as well, just to make sure that it works effectively.
Do you have any, are there any other concerns about the product, like, let's say, bar the price? Are there any pitfalls to using this type of technology?
That's a good question.
Is it just good stuff?
I'm struggling to see it.
Yeah, I suppose I'm coming from I'm looking at it there. I mean, the figures you presented at the start there, the 3.5% of the emissions, or the methane emissions, are coming from manure storage. So this is tackling a relatively small portion of that, but there is an ammonia component here as well, isn't there?
Yeah. So. Yeah, the 3.5% is small relative to some of the other emission sources. But if you were to reduce your greenhouse gas emissions, let's say by 3%, that's dramatic in terms of achieving these 1.5 degree savings or whatever else. And so yeah, the danger, I guess, is that we just settle there and say, okay, we've done the slurry bit and just leave it at that. Yeah. You saw there the enteric emissions are over 20% as well. So we do want to look at feed additives and tackling enteric emissions, because especially in an Irish context where animals are out on land more, this mightn't be as good or as relevant. So you do need to also look at enteric emissions. In other countries where animals are kept indoors all day long and they have higher temperatures and all that, this may be even more applicable. But the danger is we just kind of settle and say, okay, we've tackled slurry and we can see an effect, and then we don't step on from there. But we need to push on and really make agriculture sustainable so that we can just have a continuing industry.
That's a really important point. I mean, that 3.5% is particularly low in Ireland because of the outdoor pasture-based systems that we have in this country. So no doubt it will have a higher impact in those other countries. Pat, back to you.
Yeah, no, there's a question in relation to the verification of the potential emissions and trying to get it potentially accepted as part of our inventories. Yeah. Are you working towards that?
We are, yeah. We're working with, there's a couple of different verification bodies, and we're engaging with 2 or 3 of them. So that's part of the process before launching this on the market, is to have a verification in place. So we're talking to 2 or 3 different bodies that do verification of greenhouse gas emission savings.
Yeah, and I suppose another issue that's kind of in the new, or not so much in the news, but engaging people a good bit at the moment, is the nitrogen value of the slurries coming out. Yeah. Shaun, have you tested the nitrogen and other constituent parts, or I suppose it's going to be particularly nitrogen, to see is there a difference, and the availability then of that nitrogen, is it showing any difference?
Yeah, so we did a suite of tests on all of the slurries that we were testing. At the very start of the project, the ammonia emissions were higher, and that was simply down to the way in which we were actually adding the treatment to the slurry. However, ammonia is more of an engineering problem rather than a microbial problem. So once we had that kind of engineering problem fixed, we had that ammonia problem under control. What I will say from my own experiments is that we had a neutral impact on the available TAN, total ammoniacal nitrogen. So from that point of view, there's very little impact on the actual nitrogen in terms of losing it as ammonia.
So in general, you're saying the slurry will have a very similar value to the existing slurry. It's not because it's holding on to or losing less. You're not getting a significant boost.
So
we did carry out pot trials on slurry that we treated in NUIG as well, and we did see an increased dry matter from the grass after a single application of slurry that had been treated. So that's still open. It's one of the questions we have still. We intend to do more field trials and test it and get solid results on that as well. So.
And just a question there, what's your kind of timeline that potential for coming to market if things go well across the project?
So we'll be hoping to, within the next 2 years, have both the cattle slurry and the pig slurry treatments available on the market. So that's the intention. So we have some funding secured to bring it to market essentially now, and we're going through all the appropriate steps to do that.
And I suppose importantly, you see this as being something which is not going to take a huge amount of effort at farmer level, that you're working on systems for application that will effectively work pretty much on their own without huge managerial content or managerial effort involved.
For sure. As we know, farmers are busy as it is, and so something that's going to be labor intensive isn't going to fly. So we want to make it as user friendly as possible, and that's what we're working on now, just kind of automating application, and that's going to be a key component of the treatment as well.
I just want to make just an important clarification there, that the figure 3.5% that I quoted, I thought it was 3.5% of agricultural emissions.
No, it's
in fact, it's 3.5% of total emissions. Yeah. So that's a really important distinction to make here, is that this figure, or this technology, has really a huge potential to reduce the total emissions from agriculture.
One final question, one possibly important one: the viability of AD in Ireland has always been problematic, and I think with a development like this, and with what's happened, I suppose, with prices over the last while, do you see this as having having the potential to give a major push to that industry in Ireland?
Sure. So something significant that's happened in the last year, I do some work with Green Generation in Nerney in County Kildare, and we've received these international sustainability carbon credits, which makes the gas that we produce far more valuable. It's far more valuable now than it was, and so AD itself is now far more viable than it was even a year ago in an Irish context. And then any slurry you use for AD, it gets a double bonus essentially under the Renewable Energy Directive too. So that again makes it far more viable. If you were just treating slurry and not using any co-digestion products with it, you probably wouldn't produce enough gas to make it viable. But when you factor in carbon credits, which are there and available and in play, they're not theoretical, they're physically there in place. And then you talk about a 30% increase in gas produced from that slurry as well, then this makes it far more viable for sure. Yeah.
Okay, thank you.
Right, there we must leave it. We're just over time, I'm afraid. Lots of huge interest in this topic, and maybe Stephen and Shaun, you could join us next year when you're, in the market, and just to get that feedback from farmers would be excellent. I think a product with huge potential from the figures that you presented today. So thank you both for the time that you've put into your presentation, and Pat, thanks very much for helping with questions. And next week we'll be joining you next Thursday rather than Friday, given the week that's in it, and we'll be joined by Elaine Cross, who is Corporate Affairs Manager with Danone, and she's going to be telling us about the Danone sustainability story. So really looking forward to that presentation next week. My thanks to Andy Boland, Yvonne Marr on our production team, and also to Michelle Lavelle and Nuala Cully on our connected team for looking after the background technical piece as well for us. So until next Thursday, thanks again, Stephen and Shaun, and we hope you enjoy your weekend. And what better way to start off the weekend than be talking about slurry. So we will see you next Thursday, and do take care. Thank you. Bye-bye.
You've been listening to the podcast version of the Teagasc Signpost Series, the weekly webinar that promotes and examines sustainability in Irish farming. Don't forget to join us live every Friday morning for our latest webinar. For more, visit teagasc.ie. And you can also rate, review, and subscribe to the Signpost series on Apple Podcasts, Spotify, or wherever you get your podcasts from. I'm Mark Gibson, and thanks for listening.